So we have a pretty normal bicycle tire. It's ratcheted so that it'll spin freely this way, and the handles will rotate freely as long as it spins that way. So I will spin it. It's pretty heavy, 10 pounds maybe. I can weigh it, and I'll put it in the description, the mass. And it's got a little rip cord to get it going. Pretty good. So the first thing we're going to do is I'm going to hold it like this and spin it in a counterclockwise direction, looking from the top. So then, using the right hand rule, the angular momentum will be up, and angular momentum is conserved as long as we have rotational symmetry, which we do. We're on the Earth, so if we rotate around about an axis that comes from the center of the Earth through this thing, then we have rotational symmetry. No matter which way we look, north, south, east, west, things are the same. If we change up and down, then things get different because of gravity. But it's the same thing like with linear momentum is conserved as long as we're in a 2D plane, because if we move around side to side, everything is symmetrical. That's why you can look at balls on a pool table and they all have conservation of linear momentum, but we don't have billiard tables on the wall because it doesn't work as well with gravity and such. So I'm going to start this spinning this way, so we'll have angular momentum pointing up, and then I'm going to flip it over suddenly, so it'll still be spinning in the same direction, but now the angular momentum will be down. And I'm going to try to close myself off from the world and make this a closed system by putting my feet up on this little footrest, and I'll be free to rotate. And we'll see how the system wants to conserve, how it acts to conserve angular momentum. So this is mass that's constrained to move in a circle. Normally it would want to go in a straight line, but now it can't because of these strong steel rods. So it's going to move in a circle. Let's see what that means for the motion. And this ripcord needs to be primed. All right, let's go. Oh, it's wound the wrong way. Okay. Take two. Okay, got the ripcord wound the correct way, so let's let her rip. And a special stool, and we said we're going to start it clockwise, looking from the top. This is awkward. I need an assistant. Okay, clockwise from the top, and then I'll flip it over. And now my motion was not quite enough to carry me around because of the friction, but was also looking down, counterclockwise from the top, excuse me. Now the wheel is moving clockwise as looking from the top. Flip it over, and I'm moving clockwise from the top, while the wheel is now moving counterclockwise looking from the top. Okay, so we can use this ratchet to get it back up to speed. And now I'm going to hang it, I'm going to orient it vertically so that the angular momentum is pointing off to the side. And there's a little piece of rope here, so I'm just going to support it from one side only and see what it does. It precesses around. Instead of falling down, it's falling in a slow spiral. So gravity wants to apply not just a force down, but a torque down. It wants to rotate it down. And this is the funny spiral path it takes there. Without the friction, it's super easy to hold like this because the angular momentum is resisting that torque. So if it was a planet without friction, oh, you can't see my head this whole time? Then it would continue just to spin around indefinitely for a much longer time, like the planets do, have these funny spin around in a circle. Get it back up to speed. Let's see if it can pull me around with it. Okay, just to make sure there's no funny business, if it's not spinning and I support it on one side, then yes, it falls.